So this is, chapter 5. I believe all the ones that I have selected at the moment are out of the back of the book. So this one's number 18. And so 18 says that we have a bag of cement whose weight is Fg, hangs in equilibrium from 3 wires as shown in the figure. 2 of the wires make angles theta1 and theta2 with the horizontal. Assuming the system is in equilibrium, show that the tension in the left-hand wire is given by this formula. So this is an example of a symbolic problem. And what we should recognize is that, when physicists and engineers solve problems, they always solve them symbolically first. And then we essentially plug numbers in at the very end, if there are even numbers to plug in. And so we need to kind of practice to get good at that. And you've seen those in the homeworks that I ask, several symbolic problems here and there, so we can start to build some practice with that, and that it's not all just numbers. Okay. And so we have one wire came down like this from the figure. The other wire goes out like this. Oops, I guess I'll extend this. So, and then from here, a vertical wire, and then I guess we have some sort of band that then holds the bag of cement. All right. And so they have marked in the diagram that this one angle is theta1, that this angle with the horizontal ceiling is theta2, and that we want that the tension in this wire is 1, and that this one is 2, and that this one is 3. So I'll mark that in just a moment. Okay. And so let's go in, and what we're going to do is we're going to talk about what to do. So this one is in static equilibrium. So this is an example of a static equilibrium problem. And we can tell that because there's essentially, no motion. Okay. And since we're in static equilibrium and there's no motion, then our equation will just be that the net force is 0 in any of the component directions. Okay. Now, what we'll probably think to start with is that if we came in and we looked at the bag of cement as our object of interest, okay, then we could indicate the forces that act on the bag of cement. Okay. And so then what we would get is that there would be the gravitational force, which goes vertically down and has a value of Fg, they said. I'm going to do the big G on that one. So they didn't say it was M times G, but they just said write everything in terms of this magnitude, Fg. Then when we look at the bag, we have gravity as our non-contact force, and then everything else comes from things that touch the bag of cement. The only thing touching the bag of cement is this vertical wire, which they labeled as 3. And so then we're going to have tension in that vertical wire. It's going to run along the wire away from the object, so away from the bag of cement. And so I'm going to mark this as the force of tension 3. Now, this is the drawback to doing the notation that I prefer with the subscript to indicate the type, is that then when you have repeated forces of the same type, then it's, leads to unfortunate numbers of subscripts, but I still do prefer this one in general. And so then what you have is that these are all the forces. Now you could make your way down the list, and gravity was first and normal was second, but there are no surfaces of contact. Since there are no surfaces of contact, there's no friction of either kind. And then you get to the tension and the applied force and the spring force, and then, air type of forces. And there aren't any of those. And so now we've indicated all of the forces on our object of interest. So this is my, object of interest is the bag of cement. And then what we'll do is we'll indicate the acceleration, because, why would we do just the left side of Newton's second law, we should also do the right. And so since there is no acceleration because it's in static equilibrium, then we can go ahead and normally we would pick the coordinate system to align with the acceleration, but since there isn't any, then we'll pick the coordinate system to align with the forces. And so then since they're only vertical, then I'm going to go ahead and state that this is the, plus y direction is vertically up. And we'll go ahead and write down, Newton's second law in that vertical direction. So for the bag of cement, then what we get is that the net force in the y direction is 0 because it's equilibrium. And so then I go in and I'm going to write down the first force. I'm going to write the direction as a plus or sign, and then I'll write down the magnitude of the force. And I always do it symbolically first. So I'll do that this is plus the force of tension 3 minus our force of gravity. And then what I would do in the next line is I would put in any values that we know for these magnitudes, whether they're mg's or numbers or whatevers. And the reason that I do it this way is because I want us to focus on the directions, okay? Because that's the place where the mistakes are going to happen. And so this is representing that that vector went up and that this one went down. So those are the directions, and these are meant to be the magnitudes. Notice how they do not have the extra line on the symbol. Now, since they gave Fg as a given value, then we can solve for the tension in the third string in terms of that Fg. So then force tension 3 is our, Fg, okay? And so there we solve for that tension. Now, the thing is that by analyzing the bag of cement, then we only got the tension in the vertical string. We didn't get the tension in either of these angled strings, okay? And so then what we find is that that means that we didn't really analyze the best object, okay? And so what I always talk about in these problems is that when we're doing a static equilibrium problem, very often what we analyze is not the objects that have mass, but we analyze things like the central connecting object. And the thing that ties all of the strings together is essentially this knot, okay? And so then what we'll do is we're going to go in and look at this as our, central connecting object. So that's going to be our object of interest, is the knot. It's the thing that ties all the pieces together, okay? Now, normally we wouldn't analyze the knot because it's not going to have any mass. Therefore, it wouldn't have any gravitational force, but because there is no A, then having a 0M is perfectly fine, okay? And so that's essentially how that goes. And so when we look at the knot, then what we get is in this vertical string, we're going to have a tension force that runs along the string away from the object, which is the knot. So this will be my force tension 3, like so. And then I'll have that this is going to be my force tension 2. And it goes along the string away from the object. So we'll do force tension 2. And then I'll have this tension force here, again, along the string away from the object, which is the knot, okay? And so then this will be, force tension 1, okay? And again, what we have, it's a static equilibrium problem. There is no acceleration on the knot, so A will be 0. And so now what we want to do is we want to go in and pick out a coordinate system in which to find our components for our vectors. So I'm going to put the origin of the coordinate system at the knot. I'm going to go that up is the positive y direction. And I'm going to go to the right is the, oops, kind of missed a little bit, the plus x direction. Quite a bit of shoulder in that one. Oops. There we go. Now, what we'll need to do is we'll need to go in and find our components for these tension forces. Okay, and so I'm going to go ahead and draw in the component triangles. I think they're very visual, and when we first start, I think that's quite nice. Eventually, we'll go into the more open component pictures, and I regret putting A equals 0 right there. Right now. All right, that'll be all right. We'll go like this. And so then this will be the force, tension to, this is the Y component, and this is the force, tension to, this is the X component. And then we'll cut over like this for the X component on force, tension 1, force, tension 1X. We're going to go up like this for the force, tension 1Y. Go. Now what we need to do is we need to get some of our angles into those component triangles, okay? And so we're just going to do a little geometry in order to, make that happen. This is the point where you go, oh, I should have drawn the picture like this instead of like that. And so, like I said, very often you might need to redraw your picture. So I'm essentially doing that right now. All right, so what I'm going to look at this triangle here. It's a nice right triangle. And so then if this angle is theta 1, then this angle down here I'm going to mark as phi 1. And it's going to be 90 minus theta 1 because they sum to 180 degrees. So what we get is that our, phi 1 angle will be 90 minus theta 1 like so. And then what we have is that this is perpendicular to that. So this y-axis is perpendicular to the negative x-axis, so the plus y-axis. And then if this one is phi 1, then this would be 90 minus phi 1, which will give me back theta 1 again. So then theta 1 sits here in that component triangle. Okay? And then if we repeat that, it'll be symmetric to give us the same thing, but with the 2's. So we'll come up, we'll head over along the wire. It is a right triangle. So then my angle here is going to be phi 2, sorry. Oh, and I changed the phi. There we go. We'll make it like this. And you could picture if this is 30, this is 60. If this is 60, that's 30. I mean, for some reason, 30s and 60s always appear to be more obvious than symbols, thetas and phis or whatnots, but that's the way it would go. And again, it could be the similar kind of thing. If this is 30, this is 60, this is 60, then this angle down here has to be the 30. Theta 2. Now, what we can do is we can go in and can write down our components in terms of these, unknown angles. And so then when we go in, we find this y component. Since it's opposite the theta 2, it'll be the sine function. So it's going to be the magnitude ft2. Since it's opposite, it's going to be sine of theta 2. And for the x, it's adjacent. So this will be our ft2. Adjacent makes it the cosine of theta 2. And then for the y and the x, we're going to get pretty much the same kind of thing. So this will be my ft1. Since it's opposite the theta 1, that'll be sine of theta 1. And then this will be ft1. Since it's adjacent, it'll be the cosine of theta 1 is going to be our, ft1x. Okay. Now what we can do is we can go in and write down some of the forces in the x direction, some of the forces in the y direction. They're going to be equal to 0 because it's an equilibrium problem. Okay. So let's go in. And so then for the knot, so this one was for the bag of cement. And now what we're going to look at is the of interest is going to be the knot. Okay. And so then what we'll want to do is we'll want to go in and do our, sum of the forces in the X and then the sum of the forces in the Y. Okay, so in the Y direction, so let's take a look at that one first. Then what we're going to get is I get this force tension 1. The Y component goes up. I have this one plus the force tension 2. The Y component goes up. But then I have this force tension 3 goes down. Okay, so I put them in so I can focus on the directions up and down. And then these are going to represent the magnitudes, and we worked out equations for those magnitudes. And so with force tension 1y, this was our Ft1 sine of theta 1, plus, and then this is Ft2 sine of theta 2, and then this is minus Fg equals 0. Okay, now we'll need to remember what we're looking for, and we were supposed to solve for the tension in the wires. Let me read again. Assuming that the system's in equilibrium, so the tension in the left-hand wire is T1 given by some formula. Okay, so we want to solve for these tension magnitudes. So they gave us Fg and they gave us the thetas. So my unknowns are Ft1 and Ft2 at the moment. So I have two unknowns in this equation. So then what we're going to do is we're going to go in and take a look at the X direction. Okay, and see what we can come up with there. So let me put that here, I think. So we'll do sum of the forces in the X direction is 0. This is again on the knot. And so in the X direction, I just have this tension 2 and tension 1. To the right, I get plus force tension 2x, and to the left, which is minus, I get force tension 1x equals 0. When I plug in my values, then this is going to be that magnitude of tension 2 times the cosine of theta 2, and then this will be minus, and this will be force tension 1 cosine of theta 1 equals 0. And so then what I can do is I can use this to solve for one of the tension magnitudes in terms of the other. I can plug it into this equation and get my solution. Okay, so that's going to be the process that we're going to look at. Okay, and so then since they specifically said in the problem they wanted to find tension, so what that means is that in this equation, I'm going to solve for the other unknown. I'm going to solve for tension 2 in terms of tension 1. Then when I substitute it here, I'll have an equation only in tension 1, which was the one I wanted to find. So we're going to go in and solve for tension 2 in terms of tension 1. So I'm going to move this to the other side and then divide. So what we get is that force tension 2 equals my force tension 1 cosine of theta 1 divided by the cosine of theta 2. Okay, and then what we will do with this is I will then take this result and plug it into this equation here to get an equation only in force tension 1. I'm going to go ahead and move this Fg term to the other side. Okay, and so this is our force tension 1. This is sine of theta 1 plus, and then this will be my force tension 1, and this will be cosine of theta 1 over cosine of theta 2 times the sine of theta 2 equals our Fg. Okay, now what I can do is I can factor this Ft1 out because it's a common factor in both terms. Notice what we have are two terms because they're being added. And so then this becomes a common factor that I can factor out. Okay. The other thing that I see is I have a denominator. I can clear the fraction if I multiply both sides by cosine of theta 2. So we'll do that. And so then when I do those two steps, then what I get is that this is my force tension 1 magnitude. We're going to have multiplied by the cosine of theta 2. So I get sine of theta 1 cosine of theta 2. and this will be plus, and then the cosine of theta 2 multiplication will cancel that denominator, and I'll get cosine of theta 1 times the sine of theta 2, and then this will be equal to FG times my cosine of theta 2. Okay, then I can just divide here in order to get my result. Okay, and so then what we get is that therefore force tension 1 is this Fg cosine of theta 2 divided by the sine of theta 1 cosine of theta 2 plus the cosine of theta 1, the sine of theta 2. And then what we get is that this is essentially a trig identity. And so it's the sum angle identity for sine. Okay, so there are a couple of trig IDs that I know. Actually, I know 2. And then what happens is I know how to get every other one from those 2. Okay, so the 2 that I know are the sum and difference angle identities for both cosine and sine. So these are the ones that I have memorized. So the cosine of like A plus or minus B is cos cos sine sine. And when you add, you subtract, and when you subtract, you add, so the signs flip. The other one that I know has memorized is sine of A plus B. So this is going to be the sine, cosine, cosine, sine. So sine of A, cosine of B, then it's cosine of A, sine of B, and plus is plus and minus is minus. So it's the cosine that flips, but the sign stays the same. And so then with these 2 memorized IDs, I can get every other trig ID from them. And so I think that's a better way to kind of remember your trig IDs. You know, if you're in a situation where you need to, you know, do these from memory, then this is the way to go, in my opinion. And if you need me to show you how to do that, I don't mind doing that. Okay. Because it's easy to remember what steps you take. It's hard to remember where the heck did those 2's go, and was that a plus or a minus in the IDs, okay? And so being able to reobtain all of them is essentially the best option, in my opinion. And so then when we look at this, we get, you know, the sine of A, cosine of B, plus the cosine of A, sine of B kind of stuff. So that's the sum, the angle, sine of the A plus B. Blah, blah, blah. Words are not coming today. So this is sine of theta 1 plus theta 2. Okay, and then if we go in and look, then tension 1 was supposed to be Fg times the cosine of theta 2 divided by the sine of theta 1 plus theta 2. So this is indeed the thing we were supposed to show for the magnitude of tension 1. Okay. Now, if we wanted to, we could also get tension 2. Let me show you that. It's not that hard. We would go back to this equation that we solved. And so then I get force tension 2. I mean, they didn't ask for it, so we technically don't need to do it, but it's kind of nice to practice. Okay. And so then if I plug in what tension 1 was, this was force gravity cosine of theta 2 over that sine of theta 1 plus theta 2 times my cosine of theta 1 over the cosine of theta 2. So those cancel, and then we have the expression for force tension 2 is that Fg value times, in this case, the cosine of theta 1 over the sine of theta 1 plus theta 2. So then this becomes the answer for tension 2. And tension 3 was just Fg. So that was this one way back here. So what we were able to do is solve for the tension all 3 wires in this instance. Okay. And so then what we'll find is that, you know, this is a very simple example of, you know, a problem that would be, you know, something that like a structural engineer or an architectural engineer might end up doing. This is a very simple statics type of problem for engineering purposes. And what you get is that the tensions of these angled wires end up being larger than the weight of the object. So if we needed to wire something up like this, we need to be somewhat careful because these wires end up with more tension than the weight of the object. And so what happens is that you then need wires that are strong enough so that they won't break once you load them with the object. And so that's why they would figure out what all the tensions are and how that would go, what wires would be suitable, how big, what materials, how big of the gauge would they be, how would we tie this knot so that it doesn't untie, do we need to reinforce these points at the ceiling, all sorts of good kind of questions like that. But this is just a very simple example of something along those lines. And what I think that's interesting about this is that we ended up analyzing the knot and not necessarily the bag of cement. Now, the bag did help. I mean, we needed to do that part, don't get me wrong, to get tension 3. But technically, to get the tension in the other 2 wires, since they weren't attached to the bag, we needed to analyze the knot. So I always call that the central connecting object. And it's the thing that brings, connects all the stuff that we're looking at in the problem together. And even though it has no mass, it's perfectly valid under a static equilibrium problem because there was no acceleration. And so that's an interesting point, I think. Because normally in most of our problems, we'll analyze the things that have mass. That's kind of the way that ends up going. Okay?